on carbon and the other on oxygen. Okay, let us see. So in this structure, the carbon atom is having the lone pair of electron. So first we are discussing about the MOED diagram of the carbon monoxide. Already we know that the atomic number of carbon is 6. So its electronic configuration is 1s2, 2s2, 2p2. And the atomic number of oxygen is 8. Its electronic configuration is 1s2, 2s2, 2p4. So once you see here, so these are the atomic orbitals. Okay, these are the atomic orbitals of the carbon, and these are the atomic orbitals of the oxygen atom. Okay, so here please listen carefully. So in this is the 1s2 orbital. So this is belongs to 1s2, 2s2, 2p2. Okay. So this is 1s2 of oxygen, 2s2, 2p4. Okay. So in this structure, look at this. So this is called as MOED diagram. In this MOED diagram, we can distribute the electrons in the energy levels. So here this is 1s orbital. So this 1s orbital, already we know that in a molecular orbitals, HOMO orbitals are there, LUMO orbitals are there. HOMO is nothing but highest occupied molecular orbital. These are having the lower energy level. Just see, first we are discussing this, then only I can explain it. So actually, a molecular orbital, it is converted into two. That is, one is HOMO, another one is LUMO. HOMO is nothing but highest occupied molecular orbital. So these all are maximum filled with the electrons. LUMO, it is called as lowest unoccupied molecular orbital, and it is having the higher energy. It is having the, this HOMO is having the lower energy and LUMO is having the higher energy. Based upon that, the electron should be paired. Okay. So this same phenomena is takes place in the 1s orbital, 2s orbital, as well as 2p orbital. Look at this. So here, in this carbon monoxide, so this these are belongs to carbon electrons configuration, and it is belongs to the oxygen atom electrons. So in carbon, the 1s orbital, it is having the 2 electrons, 2s also 2 electron, p also having 2 electrons in the carbon. In this oxygen atom, the 1s orbital is having the 2 electrons, 2s orbital is having the 2 electrons, and the p orbital is having 4 electrons. The total number of electrons are 8. So these are explained by the MOED diagram. So in this MOED, this one is split into two energy level. The bottom one is called as the lower energy level and the upper one is called the higher energy level. So in 1s orbital of the carbon, it is having the 2 electron, and 1s orbital of the oxygen also having 2 electrons. Totally 4 electrons are present. So in these 4 electrons, the 2 electrons are filled in the lower energy level and 2 electrons are filled in the higher energy level. Okay. Then next, to look at this 2s orbital. In 2s also, 2 electrons are present for the carbon and 2 electrons also present for the oxygen atom. So in this, this is the lower energy state, this is the higher energy state. The first, the electrons are filled in lower energy, then enter into the higher energy level. Okay. Then look at carefully about the p orbital. So it is clear to all, I hope. Hello.
Yes, ma'am.
Adamotundamma?
Yes, ma'am.
Okay. In this p orbital, it is splitted like this. All of you write this. It is somewhat difficult in your book. Okay, so this is the p orbital's energy profile diagram. In this, here the bottom one is called as 2p x, 2p y. Okay, then this one is 2p z. Then this one is, sorry, the pi 2px, pi 2py, pi 2pz. This one is pi star 2px, pi star 2py. Okay, these two are, I write here, pi star 2px, pi star 2py. Okay, in this, in p orbital, in the carbon atom, it is having the 2 electrons and so here in this p orbital, the carbon atom is having the 2 electrons and oxygen atom is having the 4 electrons. So in this, total number of electrons are from the carbon and oxygen is 6. So first, the electrons are filled into the lower energy level, that is 1, 2, 3, 4, 5, 6. Okay, total all the electrons are filled into the only lower energy level. There is no electrons in the higher energy level. Okay. So this is the filling of the orbital. So in this filling, first the sigma 1s, it is having the 2 electrons. Then sigma 1s star, sigma star 1s, it is having 2 electrons. Then sigma 2s also having 2 electrons. Then after sigma star 2s also having 2 electrons. Then pi 2px having 2 electrons, pi 2py having 2 electrons, pi 2pz also having 2 electrons. Okay, this is the filling of the electrons in the orbitals. Once I repeat it. So the electrons are filled like bottom to top. The first one is sigma 1s to sigma star 1s2. Next sigma 2s2. Then sigma star 2s2. Okay. Then pi 2p x2 equals to pi 2p y2. Then pi 2p z2. Look at this. The s orbital is 1s orbital is having the 2 electrons plus 2, 4 electrons. P 2s orbital also having the 4 electrons, and total p orbital are having the 6 electrons. So the total number of electrons are equal to 14 electrons. So by using the fill of these electrons, we can calculate the bond order. How we calculate the bond order? That is, so the bond order is equal to half into bonding molecular orbital minus anti-bonding molecular orbital. So here the star containing orbitals are called as anti-bonding orbitals. Without star are called as bonding molecular orbital. So without star mark, the 1s2, 1s orbital is having 2 electrons, 2s orbital is having 2 electrons, and pi 2px2 having 2 electrons, pi 2py2 having 2 electrons, pi 2pz2 also having 2 electrons. So the total 1/2 into 10 minus anti-bonding orbitals are nothing but the star containing orbitals. Just it is for remembering. So star containing orbitals are 4. 1s orbital is sigma star 1s2, sigma star 2s2. So totally 4 electrons. So that is equals 1/2 into 10 minus 4, 6. Okay. Then 2 into 3. So the bond order of the carbon monoxide is 3. That means the carbon bonded with oxygen with the 3 bonds only. Okay. So this is about the MOED diagram of the carbon monoxide. Hello? May I audible clearly?
No, ma'am, it's sometimes disturbing me.
Understood?
Presenting.
Hello?
Yes, ma'am.
Okay.
आपके audible तो काफी ठीक से नहीं आ रहा.
Okay. So this is about the carbon monoxide MOED diagram. Understood? So in this, once I repeat the sigma orbital, the bottom one is called as sigma 1s as well as sigma star 1s. These are sigma 2s. In this, they are not give properly. Sigma 2s, sigma star 2s. Okay. Then in that p orbital, it is classified into higher energy, lower energy. In lower energy, the lowest one is pi 2px, pi 2py, and pi 2pz. Then the above one is pi star 2px, pi star 2py, pi star 2pz. So in this, the 1s and 1s star both are filled with the 4 electrons totally, and 2s sigma star and 2s sigma, it is also filled with the 4 electrons, and the p orbital containing pi 2px, pi 2py, pi 2pz. Each carries 2 electrons. Total number of electrons are 6. Okay. So the total number of electrons contributed by the carbon and oxygen is 14 electrons. Okay. So in this 10 are the bonding molecular orbitals electrons and 4 are the anti-bonding molecular orbitals electrons. So the bond order, it is having one equation, that is 1/2 or half into bonding molecular orbital minus anti-bonding molecular orbital. So here in this, the bonding molecular orbitals are 10 and the anti-bonding molecular orbitals are 4. So half into 10 minus 4. 10 minus 4 is equal 6. 6 it is multiplied with 2. Then the 3 is the bond order of the reaction, bond order of the carbon monoxide. And the bond length is about 1.14 angstroms. Understood? The next is about so due to the bond order 3 to produce triple bond. The HOMO of carbon monoxide molecule is an almost non-bonding sigma orbital largely localized on carbon. The LUMO is an anti-bonding pi orbital. HOMO is nothing but highest occupied molecular orbital. LUMO is lowest unoccupied molecular orbital. Carbon monoxide is a heteronuclear diatomic molecule. So why it is called as heteronuclear diatomic molecule? That means carbon monoxide, CO. In this CO, the carbon is one atom and oxygen is another atom. So these are called as heteroatom and 2 molecules are present. So that's why it is called as heteronuclear diatomic molecules. Then already we know that the electronic configuration of carbon, it is 1s2 2s2 and oxygen is 1s2 2s2 Okay, already I told that the electron filled in the orbitals. So first the electrons are filled in the lower energy level, then only enter into the higher energy level. So due to that reason, this type of structure is produced. Actually, it is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then you write it, that is pi 2px2, pi 2py2, pi 2pz2. So this type of distribution is takes place in the MOED diagrams. Then carbon monoxide is a diatomic. 14 electrons are paired up. The carbon monoxide molecule 3 sigma orbitals services as a very weak donor, and that pi star orbitals it as good acceptor orbitals. The carbon monoxide molecule is the HOMO is 3 sigma, which is largely non-bonding lone pair on the carbon atom. The LUMO is doubly degenerate pair of anti-bonding orbitals with 2p orbital character. The combination of frontier orbitals, a full sigma orbital largely localized on the carbon and pair of empty pi orbitals. Due to this, in metal carbonyls, HOMO lone pair of carbon monoxide particles is formation of sigma, and other LUMO anti-bonding pi orbitals participate in the formation of pi bond. So sigma bond is present as well as pi bond also present. So here look at this. So this is regarding for the metal atom, d orbital electron, d orbitals, and this is about the carbon monoxide. Okay, then a bond is takes place. So this type of bond is called as sigma bond. If the metal vacant orbital is bonded with the ligand empty orbital, then it produces a pi bond. It is called as backbone. Then bonding modes of metal carbonyl. So different types of metal bonds are present. Some are the normal bonds are present. Some are the bridged bonds are present. Okay. So how we can know the how we can know it is the normal metal carbonyl or it is the bridged carbonyl, it is the triply bridged carbonyl. Okay, so by using the spectra, we can know it is the normal carbon monoxide bond or it is the terminal or it is the bridging. Let us see if the IR values are at 2100, that means the common CO bond is take place. If the carbon monoxide and metal, the range, that is the IR frequency range is in between the 2000, the terminal carbon is bonded with the metal. If a bridged bond is present, then the stretching frequency vibrations are started in between the 1900 to 1800. If a triple bridge is present, then it will get 1700 to 1600 centimeter universe. Okay. So next, there are 4 types of metal carbonyl bonds are present. One is terminal carbonyls. Number 2, bridging carbonyls. Number 3, semi-bridging carbonyls. Number 4, triply bridging carbonyls. So 4 types of carbonyls are present. Let us see which one is called as terminal ligation or how the terminal bond is formed. The terminal ligation implies that a carbon monoxide ligand is bound to a single metal. Okay, the carbon monoxide ligand is bound to a single metal, and that's why it is called as a terminal ligation. So let us see. So in this, the carbon monoxide, the carbon atom is bonded with bonded with only a single metal. So it is called as terminal ligation. Okay. This is also another example, that is FeCO5. In this also the iron is bonded with the carbon monoxide and also called as terminal ligation. The next second one is about bridging ligation. Here the 2 metal atoms are there. The 2 metal atoms, okay, these are bonded with a carbonyl and produce a bridge in between the metal and carbon. Those are called as bridging ligands or bridging ligation. The next one is about so this is also called as bridging. Look at this. In this, the two iron atoms. This is the iron metal. This is another iron metal. You write here Fe. These iron metals are bonded with the bridge ligand like this. Okay. So these three ligands are called as bridging ligands. Then the next one is about semi-bridging ligation. Semi-bridging ligation is nothing but it could not produce a pure bridging bond, but it produces a partial bond. So that type of system is called as semi-bridged ligation. The fourth one is triply bridging ligands. That means the three metal atoms are bonded with a ligand and produce a bridge. Look at this. In this structure, the three metal atoms are bonded with this carbonyl ligand. So that's why it is called as triply bridged ligation. Okay. Then the next one is metal carbonyl complexes. Okay, the many of the transition metals form compounds with the CO ligand. CO is nothing but carbonyl ligand. Okay, the metal atoms are bonded with the carbonyl ligand. The carbonyl CO is a very strong Lewis base and it to form strong bonds to the metals in Lewis complexes. The metals are having the low oxidation state or it doesn't having any oxidation state. That means it is having the zero oxidation state. Understood? So the carbon monoxide, it is a strong Lewis base. And when it is formed with a bond with the metal atom is having the less or low oxidation state. The maximum, the oxidation state of the metal atom is 0. Okay, and many of the metals obey the 18 valency electron rule. Okay, by using the 18 valency electron rule, we can say that the complex, whether it is the stable or it is unstable complex. Okay, then the carbonyl complexes are divided into different kinds. That means only one metal atom is present, that is called as mononuclear compound. The two metals are there, that is called as dinuclear carbonyl compounds. 3 metals are there, 4 metals are there, 5, 6, whatever it may be. So these are classified into likewise. Okay, mononuclear, dinuclear, trinuclear, tetra, penta, hexa, as well as polynuclear hydrocarbons. Okay. So these are some of the examples of the metal carbonyls. So in this first you can see this hexacarbonyl chromium. Okay, in this hexacarbonyl chromium, only one metal atom is there. Metal is nothing but it is called as nuclear. So the mononuclear carbonyl. Okay, it is called as mononuclear carbonyl. The structure of like this. The next take is one FeCO5. In this also Fe, iron atom is present. So this iron atom is acting as the mononuclear. So it is example for mononuclear carbonyl compound. This is also nickel tetracarbonyl, or it is called as tetracarbonyl nickel. So like this, vanadium hexacarbonyl, molybdenum hexacarbonyl. So these are the some of the mononuclear carbonyl compounds. The next one is about Mn2CO10. In Mn2CO10, 2 metals are there. Metal is called as nuclear. So 2 nucleons are present. So that's why it is called as dinuclear substances. Okay. Then take this CO2, CO8. In this also the two nuclear cobalt. Look at this. CO. It is called as cobalt. Okay. If you can write C and go like this, then it is called as carbonyl. Okay. You remember this too. So in this structure, this is the cobalt metal, this is the cobalt metal, and the remaining all these all are acting as the ligands, carbonyl ligands. So in this, the two metal atoms are present, so that's why it is called as a dinuclear metal carbonyl. Then let's take the next one. In this, the two iron atoms are present. Okay, this is one iron atom, this is another iron atom, this is another iron. So three iron atoms are bonded with the metal atom. So it is called as trinuclear carbonyl compounds. Okay. This one also. In this also three metal atoms are there. Next is about the, in this structure, this is one metal, this is another metal, this is another metal, this is also another metal. So four metal atoms are present. So that's why it is called as tetranuclear metal carbonyls. Okay.
Ma'am, voice is not audible.
Hello. 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 Okay, let us take another example. Okay, that is MnCO5. Okay, pentacarbonyl manganese. In this pentacarbonyl manganese, the manganese atomic number is 25 and its electronic configuration is 3d5 4s2. That's why in outermost shell it is having 7 electrons. The 5 carbonyls donate 2 electrons, 5 into 2, 10 electrons. And the negative charge is written upon the complex. The negative charge it is requires 1 electron. So the total number of electrons are 18. So the complex, it obeys the Sidgwick theory. So that's why it is called as a stable complex. Then just like, look at this Mn2CO10. Okay, this is called as dinuclear compound. So in this dinuclear compound, first we can calculate the how many outermost electrons are present in the manganese. That is equal to 1 manganese is having 7 electrons. Totally 2 manganese atoms are there. 2 into 7, that is equal to 14 electrons. And 10 carbonyls are present. Each carbonyl can donate 2 pair of electrons. 10 into 2, 20 electrons. And in Mn2CO10, it is having metal-metal bond. That bond requires 2 electrons. So the total number of electrons are 36. So 36 for the 2 metals. So 1 metal carries 18 electrons. So each metal is having the 18. So it's obey the 18 valency electron rule. So these are the some of the other examples of the carbonyl complexes. Then let us discuss how we can prepare the nickel tetracarbonyl complex. Okay. So here the nickel atom, it is directly reacted with the carbon monoxide in the presence of the 60 to 100 degrees centigrade. It is converted to nickel tetracarbonyl. As well as the nickel iodide, it is reacted with the carbon dioxide in the presence of the copper. Then it is converted to nickel tetracarbonyl and CuI2. Then the nickel sulfide also reacted with the carbon monoxide. It produces nickel tetracarbonyl. And what are the properties of this nickel tetracarbonyl? So it is a colorless ligand, melting point with 25 degrees centigrade and boiling point with 43 degrees centigrade. Okay. So this nickel tetracarbonyl, it is a colorless substance and its melting point is minus 25 degrees centigrade and its boiling point is 43 degrees centigrade. As well as it is insoluble in water but soluble in the organic solvent. And also it is reacted with sulfuric acid to form nickel sulfate. Okay, the nickel tetracarbonyl is reacted with the sulfuric acid, then it is converted to nickel sulfate. It reacts with the moist nitric acid to form deep blue color complex. Okay, nickel tetracarbonyl is reacted with the nitric acid. It produces a deep blue color nickel nitrous acid complex. Okay, these are the properties as well as the preparations of nickel tetracarbonyl. So today class we are discussing about the carbon monoxide. The MOED diagram is the most important. So in this topic, the 3 questions are important. One is MOED diagram of carbon monoxide. The second question is 18 valency electron rule. The third question is preparation and properties of the nickel tetracarbonate. Okay. Then tomorrow we are discussing about the MOED of the nitrogen complex, how the bond is produced, and what are the types of the nitrogen complexes are formed. Okay. Tomorrow we are discussing about that one.